My presentation today is called Hyphenating GCMS, and we're looking at the GC perspective. This is a typical GCMS system. So this is a gas chromatograph on the left-hand side, just around here, which is hyphenated through the transfer line shown here to the mass spectrometer on the right-hand side. And, of course, it's all connected via a computer. Now, this is two instruments, the GC and the mass spec, and they are both different techniques. So when we were looking at GCMS, we have to optimize the gas chromatography and also the mass spectrometry. So the mass spectrometer on the right-hand side will influence the parameters that we put into the GC, and the GC parameters will influence the mass spectrometer. And that's what we're going to be looking at today in our two presentations, first of all on the GC side and later on the mass spec side. Firstly then, GCMS, what can we use it for? We can use it to separate and then identify volatile chemical constituents present in a sample. We can use it to determine the concentration of each type of constituent. We can determine the molecular weight and the structure of the constituent by using the mass spectrometer. We do have two techniques to optimize. Firstly, the gas chromatograph. We should be optimizing that with a mass spectrometer in mind. And then the mass spec method should be optimized bearing in mind the separation of the analytes by the gas chromatograph, and depending on the peak width those analytes are eluting. The best method, the most robust method, will be by optimizing both parts of the GCMS method. Firstly, the chromatographic resolution on the gas chromatograph, and then the analytical resolution on the mass spectrometer. And this will give us high-quality data, which means that we'll get accurate and true results. First of all, let's take a look at the GCMS instrumentation. We first of all have our mobile phase, which is our inert carrier gas. And this moves from the source of the gas over on the left-hand side, that could be a cylinder or a generator, through a series of lines and traps, enters the GC, usually through an EPC connected to the GC inlet, then travels through the analytical column, and finally into the detector, which is the mass spectrometer in this example. When we go to inject our sample, it could be through our autosampler. Our sample is vaporized in the GC inlet and then is transferred and separated through the analytical column and then flows into the mass spectrometer. The carrier gas type and flow, let's look at that to start with. The main carrier gases used in GC are helium. This is the most common, but it's getting very expensive now. Hydrogen is becoming much more common, but we do have to use it with caution. It is reactive, especially when we use a mass spectrometer which has got a hot ion source, and it can be used, can cause hydrogenation of certain compounds. Nitrogen is generally not used in temperature-programmed GC, and therefore it's very rarely used with mass spectrometry. When we're thinking about optimizing our flow rate, we should be optimizing it with the mass spectrometer in mind, depending on the pumping capacity of the instrument. If we have a look over here at the Van Demeter equation, we can see that we've got nitrogen, which flows at quite low flow rates to give it an optimal flow at this point here. But as I said, generally nitrogen is not used with temperature-programmed GC. We look at helium, which is the pink line just here. We can see that the optimal efficiency is when we're using a flow rate or an average linear velocity of approximately 20 centimeters per second. But we can gradually go up to higher flow rates too, and still continue to get a good separation efficiency. When we look at hydrogen, the optimal flow rate for that is much higher, up towards about 35 to 40 centimeters per second. And that will give us the optimal separation. So we can still use even higher flow rates there to get a very good separation, But as I said, we do have to bear in mind the pumping capacity of our mass spectrometer, and this depends on the vacuum system. So knowing the pumping capacity of our mass spec vacuum system is very important to then get the best flow rate for our separation, but without reducing the sensitivity of the mass spectrometer. So we want to make sure we've got a low enough flow rate to maintain a good vacuum and therefore keep our good sensitivity with our mass spec method. We could install 2 columns into the mass spectrometer. That can be very, very useful for certain applications, but in order to do that, we'd have to maintain flows through both of those analytical columns. And therefore, to do that, we need to make sure that we've got a very good vacuum system with a high pumping capacity. So when we're thinking about our carrier gas purity, of course, mass spectrometers are very sensitive instruments. So therefore, we need to be using a carrier gas that's got a high purity of grade 5.5, which is 99.999% or higher is recommended. Our cylinder of gas containing our carrier gas might be very, very pure. But of course, transporting it between the cylinder, which could be outside, all the way through the building into our instrument, it could pick up contaminants through the lines. So therefore, using traps and filters immediately at the back of the GCMS instrument will maintain the high purity of that carrier gas. Ideally, we should be looking to remove moisture, oxygen and hydrocarbons from our GCMS carrier gas. Oxygen and moisture can damage stationary phases, and of course, moisture, oxygen and hydrocarbons can reduce the sensitivity of the mass spectrometer. We also need to make sure that we check all gas plumbing lines regularly for leaks. Now, when we're analysing our sample through our gas chromatograph, there could be different ways that we control the flow rate through the analytical column. In constant pressure mode, the head pressure is held constant throughout the GC run. This can result in peaks broadening towards the end of the run. And that is because as our temperature in our GC oven increases, the viscosity of the carrier gas decreases. That results in overall reduction in column flow. And that's when we're holding pressure constant. Therefore, as the flow rate reduces through the column, the peaks will take longer and longer to elute, and as they're spending more and more time within the analytical column, they will broaden. Also, with mass spectrometers, large changes in flow can cause calibration, reproducibility, and other stability issues. So therefore, we don't want a large change in our carrier gas flow rate into the mass spectrometer. If we regulate the flow of gas through the column in constant flow mode, this means the electronic pressure controller will ramp the carrier gas head pressure linearly in line with the oven temperature program. So as the oven temperature program increases, the flow of gas, head pressure of the gas increases into the inlet and therefore maintains the flow through the analytical column throughout the run. This means that we maintain a constant flow of gas into the mass spectrometer. It reduces peak broadening and run times, and therefore we will maintain sharp peaks. Alternatively, we could use a ramped flow method. With a ramped flow method, we increase the flow rate through the column throughout the run by rapidly increasing the head pressure as the oven temperature program increases. This means we can obtain even sharper peaks towards the end of the chromatogram and reduce run times further because our peaks will elute faster. But again, thinking about the vacuum of the mass spectrometer, higher flows can reduce the sensitivity, and therefore we need to make sure that if we are going to increase the flow, that we don't go above the flow rate that could reduce our vacuum and therefore reduce our sensitivity. talk about sample introduction, which we will discuss in more detail in a minute, we could go and introduce our sample with either positive or negative pressure pulses at the beginning of the run. So therefore, in the first section here, we'll be transferring the sample from the inlet onto the analytical column. We could increase our pressure during that time, which would result in a faster transfer. Of course, if we use very high pressures here, this will also increase the flow rate into the mass spectrometer, which isn't a problem as long as we don't reduce the vacuum by too much, and also that we then reduce it again to when we're separating our analytes through the column and they're eluting through into our mass spectrometer, just to make sure that we don't lose any sensitivity. So, we've talked about carrier gases, how to have nice clean carrier gases, and also optimize our flow rate through our gas chromatograph and into our mass spectrometer. Let's talk about how to introduce our sample actually into the analytical column to start with. There's a number of techniques to do this, so depending on which technique we use is very much dependent on the type of sample and the type of analytes that we actually are trying to analyze. So we could, for a start, go and introduce our sample directly onto the analytical column. And this is called on-column injection, and it's usually achieved below the boiling point of the solvent, so therefore it's called cold on-column. Or we could introduce our sample into the GC inlet and vaporize it there before transferring it onto the column. So we could either do this with a hot injection. As soon as the sample is introduced, it will immediately vaporize and be transferred onto our column. A cold injection means that we inject our sample into our inlet below the boiling point of the solvent. We then heat the inlet and transfer the analytes onto the column. Or if we wanted to introduce a very large volume of solvent, we could inject that large volume into the GC inlet in cold mode. We then vaporize the majority of the solvent out of the split exit, and then we close the split exit, heat the inlet, and transfer the remaining concentrated analyte onto the column for separation and detection. So considerations with a mass spectrometer when we're transferring our analytes onto the column. First of all, the level of high involatile materials contained within the sample. If we inject our sample directly onto the column, then that dirt will all go onto the column. Even if we do a vaporizing injection, depending on the temperature of the inlet, we will still get transfer of the involatile material onto the column. And what it does is builds up onto the column and it gradually moves through. This can damage the stationary phase and cause a higher column bleed. Both of these can lead to dirtying the ion source faster as well as causing chromatographic problems. We need to make sure that the inlet temperature is optimized to transfer the analytes with the minimum involatile components. So we need to optimize the temperature so it's just hot enough to transfer the least volatile component that we're interested in. We could use a small plug of glass wool, usually around the bottom of the inlet liner, if the column would be here. It's quite useful as that is very good at trapping dirt and reducing the likelihood of it transferring onto the column. We could also choose to do backflushing. With backflushing, we reverse the flow through the column and therefore remove dirt through the split exit. That means that it doesn't gradually move through the analytical column and certainly doesn't reach the detector. When we think about our inlet, we need to think about the consumables that we should be using when we have a mass spectrometer at the end of the analytical column. Firstly, graphite ferrules, which are often used in the GC inlet as well as on the mass spec transfer line. These are porous to oxygen, so you should only be using graphite ferrules on a PTV inlet. This is an inlet which heats and cools, and therefore the graphite maintains a leak-free connection. Otherwise, we should be using either an 85% vesicle and 15% graphite or a metal seal-tight ferrule on the inlet, but certainly on the mass spec transfer line. This means that we can keep the oxygen out of the system, which reduces background in the mass spectrometer. Thinking about the septa in the GC inlet, just here, some septa are damaged by solvents. For example, dichloromethane is particularly aggressive. Damage of septa will first of all lead to leaks within the GC inlet, but also the bleeding septa, even if it's swept with a septum purge, can lead to a higher background. And as mentioned before, mass spectrometers are particularly sensitive to any background, and so therefore to get high sensitivity analysis, we need to reduce the likelihood of this. Also, as septa, the inlet seals, and also the lineless seals start aging, they will start leaking. And again, we don't want a leak into our mass spectrometer. So we need to ensure that our inlet is well maintained. When we're leak tracking our mass spectrometer, we will generally see quite a high background of nitrogen and moisture if we have our inlet in splitless mode. So therefore, we should be employing a split on about between 20 and 30 mils a minute when we're doing the leak check, just to make sure that the levels of nitrogen and moisture are below the recommended limit for actually running and using the instrument. So we've talked about sample introduction. Let's move on to the analytical columns themselves. There's three main types of analytical columns. These are packed columns, plot columns, and the most common capillary column is a wall-coated open tubular column. Now, packed columns tend to be very wide internal diameter and very short, and the best analysis, the best separation can be achieved on these columns with quite high column flows. Therefore, these are not generally used with mass spectrometers. So moving to capillary columns, these are open tubular columns. The stationary phase is coated on the inner walls of the column itself. It's just like a long, thin tube with the stationary phase coated on the inside. So plot columns, or porous layer open tubular columns, have the solid phase coated on the inside of the tube, whereas with wall-coated open tubular columns, or W-cut columns, to be honest with you, generally capillary columns is the most frequent term for these, and this has a liquid coated on the inside of the tube. This could have a siloxane backbone, or it could be something like a polyethylene glycol liquid stationary phase. So these two types of columns are the ones more generally used with mass spectrometry, but by far the most common is the wall-coated open tubular column. So let's take a better look at these W-cut phases. As mentioned just now, it could be the fact that we have a siloxane backbone within our stationary phase. An X1 or an X5 are non-polar columns, X being the manufacturer, so it could be a DB1, an HP1, a BP1, etc. These are 100% methyl groups in these two positions. These are very good for separating non-polar analytes, and they have stable phases, so high maximum temperatures. If we replace the X here with a cyanopropyl phenol, or just phenol with a high percentage, say for example 35-50%, this is a mid-polar group, and it's very good for separating mid-polar analytes. However, these type of phases can be less stable, and therefore they have lower maximum temperatures. The other type of liquid phase we can have coated in our capillary column is polyethylene glycol. This is a very polar phase. It's very good for separating polar analytes like alcohols, and it's even less stable, meaning we have a lower maximum temperature. So in general, the more polar the column, the less stable it is, and the higher bleed it gives, which of course will affect our mass spectrometer. So column bleed. As the temperature increases in the GC, the oven temperature program goes up through the run, we will generally get a higher increase in the amount of bleed. All analytical columns bleed all of the time, but the amount they bleed depends very much on the temperature of the GC oven. Column bleed will dirty the ion source in the mass spectrometer. Therefore, it will also reduce sensitivity. It will reduce sensitivity, though, particularly for certain compounds showing the same ions as the column bleed ions. It also reduces the quality of the mass spectrum, meaning that when we do library searching, we won't get such a good similarity of match, because our mass spectrum will also include the bleed ions from the column. The column bleed itself is chemical noise. It's molecules from the column phase which is causing a detector response. And as I said, it increases with increasing oven temperature. If we just did a blank run with no compounds at all injected, we would still get a chromatogram and at each point a mass spectrum. And looking at that mass spectrum, we could then examine the ions from the column, so the column bleed ions. When we then go and analyse our sample, and we have to look at the mass spectra and in particular ions that we might quite want to quantify on for particular compounds, then really we should be trying to avoid ions which are also present in the stationary phase. And that means that we'll get better signal-to-noise values for our peaks. If we want to do library searching, then we need to try and remove the background of these the column bleed ions before proceeding the library search. We can get analytical columns which are optimized for mass spectrometers. These could include phenyl groups actually within the backbone of the siloxane stationary phase itself. They're very good for mass spectrometers because they tend to be lower bleed. These will incorporate either a phenol or phenyl type group into the siloxane polymer background, and they're quite commonly called aralenes. Columns which are optimized for mass spec often have MS in the column name, meaning it's very easy to identify these lower bleed columns. There's also a new type of column stationary phase out, which are called ionic phases, and these are reported as having lower bleed, and therefore they're suitable for mass spectrometers. So we've talked about the stationary phase within the column. So what about when we're optimizing our column dimension? If we increase the column length, will it improve the separation of the analytes, because there'll be more interaction sites to produce the separation. But also, of course, the analytes will need to travel further through the column, which means that the runtime will also increase, and therefore band broadening will increase because the analytes are spending longer in the stationary phase. So therefore, when we're optimizing the column length, we should be using the shortest length possible while still getting good enough chromatographic separation between the analytes we're interested in and also the matrix components. When we're thinking about the column internal diameter, if we reduce the internal diameter, it improves the separation of the analytes, we get better interaction. It reduces analysis times. It reduces, though, column capacity as well, which means that we only can analyse less sample. If we inject too much sample into a narrow ID column, we will get overloading, and that would affect our chromatography. Larger internal diameter columns have higher optimal flow rates, and therefore they're not suitable for analysis with mass spectrometers, again, going back to the vacuum. Therefore, when we're choosing the internal diameter of our column, if it's to be used with GCMS, we would be choosing one with an internal diameter of 0.25 millimeters or less. If we wanted to use a larger internal diameter of our column, we then want to be using a restrictor to reduce the flow rate into mass spec and therefore maintain our vacuum and maintain our sensitivity. The final parameter we need to optimize and choose when we're setting up our analytical column is the stationary phase film thickness. If we increase the film thickness, it will improve the separation of the analytes because we'll get more interaction sites to get to a thicker film. But it will also increase the runtime. It will also increase the peak capacity, meaning we can analyse more sample without overloading our peaks. But if we have more stationary phase, we'll also have a higher amount of column bleed, which again is not good for the mass spectrometer. Therefore, when we're choosing the stationary film thickness, we should be using the thinnest film possible while still obtaining a good separation. In general, if we're analysing very volatile compounds, we'll be choosing a thicker stationary phase, and if we're analysing very involatile compounds, we'll be choosing a very thin stationary phase to make sure that we get the peak all the way through the column as quickly as possible. As mentioned earlier, one way of reducing the likelihood of our less volatile compounds gradually moving through our column stationary phase and into our detector, which of course will dirty our iron source faster, we could consider backflushing. In this diagram here on the left-hand side, this is where we're doing the analysis. So we inject our sample into our inlet just here. Sample will then transfer through column A. Now this could be a column with a stationary phase, or it could be a pre-column. And it will then move through the flow switch device, move through column B. Again, column B could either be the analytical column or a restrictor, and into the mass spectrometer. So we analyse our sample through our system. Then, when we get the last peak of interest onto column B, or all the way into the mass spectrometer, depending on how we have the setup, then what we'll do is we will increase the pressure into our flow switching device, vastly reduce the pressure going into the system through the inlet down to about 1 or 2 psi, and that means that then the flow rate through the analytical column will be reversed. We will still be maintaining a small amount of flow into the mass spectrometer through column B, but to reduce the flow rate, we will usually be having this with a narrower internal diameter. Therefore, the majority of the flow will flush back through the column A and out through the vent exit of our GC inlet. So if we use column backflushing, it will give us a longer column life. Therefore, the less volatile compounds are less likely to damage the stationary phase, and also less frequent maintenance. It will reduce the contamination into the mass spectrometer and give us cleaner mass spectra. It will reduce the background, so we will also minimise the noise carryover. It will give us a shorter analytical cycle time because we only have to analyse up to the point where the last compound of interest enters the mass spectrometer, and then we stop the run and enter backflushing mode, which is much faster. We can get good reliable retention. We get fewer ghost peaks and baseline drift. That's because we're removing all that heavy and volatile material from our stationary phase. Unfortunately, though, backflushing can be incompatible with some constant flow methods. The injector must have a suitable vent port for backflush exit, so usually we could only do backflush with a type of spitless inlet or PTV. And when we're using a mass spectrometer with backflushing, we're very much limited in terms of the flow rate for backflushing by the vacuum system of our mass spectrometer. And as I said, knowing the capacity of that MS vacuum system is very important, and we can minimise the flow by having column B with a narrower internal diameter. But the lower flow we use during backflushing, of course, the longer the backflushing will actually take. So therefore, being able to use quite a high flow will actually make us have a shorter run time overall. So let's think about our peak shapes going through the GC. So a good sample introduction technique will result in sharp peaks eluting out into the detector. If we use narrow internal diameter columns, will also result in sharp peaks. If we have a very highly efficient column and also a highly efficient carrier gas as well, this will also result in sharp peaks. If we get a fast separation and elution, we get less band broadening, and that results in sharp peaks at the detector. Sharp peaks generally in chromatographic separation are good because it gives us better signal-to-noise values and a higher sensitivity. But if our peaks are too sharp, we will not get enough data points across the peak if our mass spectrometer cannot analyse that data fast enough. If we don't have enough data points, we get poor integration and also poor analytical resolution or deconvolution. The worst case scenario is we actually miss the peak to start with. So when we're optimizing our GC preparation, yes, we want to have good sharp peaks, but we don't want them too sharp and too narrow that the mass spectrometer can't see them because it can't analyze, it can't acquire data fast enough to actually get enough data points across our peaks. So now, just moving through the system, let's finalize with our detectors. So mass spectrometry has many advantages, but also some GC detectors can have many advantages for some applications. So selective detectors can be more specific than mass specs. For example, we're looking at specific atoms within the molecule or certain bonds. For example, a sulfur chemiluminescence detector will analyze and see compounds containing sulfur to very high sensitivity. Some detectors are more sensitive to certain analytes or analyte classes. For example, the electron capture detector is very, very sensitive for halogenated type compounds. Other detectors, for example, the flame ionization detector, has a very large linearity range with 10 to the power of 7. So therefore, if you're analyzing samples at a very, very wide range of concentration, that's quite a useful detector to use. Also, some detectors can also produce more meaningful quantitative data. So therefore, if we're looking at total Petarian hydrocarbons, we might be wanting to be looking at an overall area rather than the area of individual peaks, and therefore an FID might be better. So when we're optimizing an application, we could consider splitting to other GC detectors as well. So we could be using the mass spectrometer, for example, for qualitative analysis and identification of compounds, but also we could be using a GC detector for more the quantitative analysis, especially very high sensitivity detectors for certain compounds. There are more than 20 GC detectors on the market, so that means there's quite a large range of choice. So yes, mass spectrometers have many, many advantages, but also we might think about using other GC detectors too. So thinking about detector selectivities, for example, we might have universal detectors. This means that they can see pretty much most organic compounds. So FIDs, TCDs on a mass spectrometer in scan mode. This, for example, might give us our top chromatogram just here where we can see lots of peaks. Great if you want to see everything in the sample. But we could also use selective detectors. So there's a range of different such detectors. Here it's an electron capture detector, meaning we can only now see analytes that are capable of capturing an electron. And these ECDs are really the most sensitive type of detector. Mass spectrometers are only now catching up with them in terms of sensitivity. We could also use a different detector as well, for example, a nitrogen phosphorus detector. Here we can see a chromatogram in phosphorus mode, and again, this is even more selective. Therefore, we could, in our application, go and split between our mass spectrometer, our ECD, and our MPD in phosphorus mode, get 3 chromatograms, 3 lots of information, depending on what we want to, what information we want to get out of our sample analysis. So that's the end of our presentation on looking at the GC perspective of a GCMS. If you have any questions.